if you didn't watch the last video because there was too much physics, I'll just quickly summarize what we talked about. We went over the Bohr model of the hydrogen atom, which has one proton in its nucleus, so here's the positive charge in the nucleus, and a negatively charged electron orbiting the nucleus. And even though this is not reality, the Bohr model is not exactly what's happening, it is a useful model to think about. And so we just assumed the electron was going in this direction, so counterclockwise around, which gives our electron a velocity tangent to our circle, which we said was v in the last video. And in the last video, we calculated this radius, right? So we calculated the radius of this circle, and we said this was equal to R1. So R1 turned out to be 5.3 times 10 to the negative 11th meters, which is an important number. And we also derived this equation, right? So R for any integer n is equal to n squared times R1. For example, if we wanted to calculate R1 again, so the first allowed radius using the Bohr model is equal to 1 squared times R1, and so obviously 1 squared is 1, so R1 is equal to 5.3 times 10 to the negative 11 meters. And so when n is equal to 1, right, we said this was an electron in the ground state, in the lowest energy state for hydrogen. We'll talk about energy states in the next two videos. Right, so this is a very important number here. So this number right here is the radius of the smallest orbit in the Bohr model. In the previous video, we also calculated the velocity, or we came up with an equation that you could use to calculate the velocity of that electron. Right, so if you go back to the previous video, you'll see the equation that we derived was the velocity is equal to the integer n, right, times Planck's constant divided by 2 pi m times r, and we figured this out using Bohr's assumption for quantized angular momentum and the classical idea of angular momentum. So if we plug in some numbers here, we can actually solve for the velocity of this electron, right? Because we're going to take this radius and we're going to plug it in down here, and then we know what these other numbers are, right? So we said n was equal to 1, so we're talking about n is equal to 1, so we're going to plug in a 1 to here, right? So this would be a 1. The velocity is equal to 1 times Planck's constant, 6.626 times 10 to the negative 34, right? Divided by 2 pi times m, and we're talking about the electron, right? So m was the mass of our electron, which is 9.11 times 10 to the negative 31st kilograms. And finally, for n is equal to 1, this was our allowed radius. So we can plug this in for our radius, 5.3 times 10 to the negative 11. All right, so if you do all that math, right? If you do all that math, I won't take the time to do it here, but you'll get a velocity approximate sign, 2.2 times 10 to the 6th, and your units should work out to meters per second, so that's the velocity. So going by the Bohr model, you can calculate the radius of this circle here. So you can calculate this radius, and you can also calculate the velocity. And again, this isn't reality, but we'll use these numbers in later videos, so it's important to figure out where they came from. All right, so this is the radius of the smallest orbit allowed using the Bohr model, but you can have other radii, and we can calculate the radii of larger orbits using this equation, right? So we're just going to use different values for n. So we started off with n is equal to 1. Let's use the same equation, and let's do n is equal to 2. So let me go ahead and rewrite that equation down here. Let's get some room. So r for any integer n is equal to n squared times r1. Let's do n is equal to 2 here. So n is equal to 2. So let's go ahead and plug in 2. So we'd have 2 squared times r1. So r2, all right, the second allowed radii, or the second allowed radius, I should say, is equal to 4 times r1. So if we're thinking about a picture, right, let's say this is the nucleus here, and then this tiny little radius here is r1. If we wanted to sketch in the second allowed one, it would be 4 times that. So I'm just going to approximate. Let's say that radius is 4 times that. So this is R2, which is equal to 4 times R1. And so we sketch in the radius of this next radius here. This is the next allowed radius using the Bohr model. we could figure out mathematically what that's equal to, because we know R1 is equal to 5.3 times 10 to the negative 11 meters. And so if you do that calculation, 4 times that number gives you approximately 2.12 times 10 to the negative 10th meters. All right, so this is our second radius. All right, so when n is equal to 2. Let's do one more. So when n is equal to 3, so let's get a little bit more room here. So when n is equal to 3, right, this radius would be equal to 3 squared times r1. So once again, we're just taking 3 and plugging it into here. And so 3 squared is, of course, 9. So this would be equal to 9 times r1. So our next allowed radius would be 9 times r1. And I'm sure I won't get this accurate, but you can just, it's a lot bigger, right? So this would be r3 is equal to 9 times r1. So I won't even attempt to draw in that circle, but you get the idea. And we could do that math as well. So 9 times 5.3 times 10 to the negative 11 meters would give you approximately 4.77 times 10 to the negative 10th meters. And so these are the different allowed radii using the Bohr model. So you could say that the orbit radii are quantized. Only certain radii are allowed. So you couldn't get something in between, right? You couldn't have something like in between in here according to the Bohr model, so this is not possible. And these radii are associated with different energies, and that's going to be really important, and that's really why we're doing these calculations. So we're getting these different radii here, and each one of these radii is associated with a different energy. So again, more to come in the next few videos about energy, which is probably more important.